Alright, so in this video we're going to be doing lesson 6.6, days 1 and 2. We're going to be dealing with the natural base of logarithms, e. So, first we need to know what e is. It's not a variable like you'd think, it's just a number, an irrational number, which is one that does not repeat and does not terminate. So it's like pi, where pi is 3.14159 blah 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 blah, and it goes on forever. Well, e is the same way, but it's 2.7182 blah 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 blah, and it goes on forever, never repeating, never terminating, meaning it never ends. So we're just going to practice first with our calculators and getting used to those. And we're going to take x equals 2, and we're going to plug that in for x into our exponential function here. So e raised to the x, but when x equals 2, so we'll plug that into our calculators. What we need to find is we need to know where our e key is. Well, our e key, or e to the x, happens to be with the natural log. It's associated with the natural log, because the natural log is log base e. But in order to get that e to the x, we have to hit the second button first. So if you're having trouble seeing what I'm doing, I have a bigger one here, so we hit second, and then natural log right here. And then we should be able to plug in the 2 for x. Now each of our calculators will look a little bit different. So some of ours will have e, and then you have like a little box, and you'll put a 2 in there. Some of ours will be e caret, and I think usually there's an open parenthesis, and we put 2 in there, and then we'll close that parenthesis and hit enter. Either way, when we plug those into our calculator, we should end up with 7.398, which should round to 7.40 if we're doing it to the nearest hundredth. So now let's do the other 2 problems, B and C. So you pause it if you're trying here, and then you can check them with me. Alright, the other 2 answers, and I'm doing these squiggly equals because I'm rounding. It's about that. We get 1.65, and we get 0.37. Alright. So our next move is the continuous compounding formula. So this is our continuous compounding formula. A equals P e to the RT. So that's something that you definitely want to write down. Now all of our variables are still the same. The only thing that's different is now we have e involved, but we're just going to plug everything in like we would do with any of our other formulas that we have. So let's try a problem. So for this one, we have P is our 1,000. Here's our percent R. We've got to change that to a decimal though, 0.076. And here's T, 8 years. So we plug that into our calculator. So we have A of 8, meaning the amount of money you make after 8 years. It's not A times 8. It's just amount of money after 8 years. 1,000 E raised to 0.076 times 8. So we plug that into our calculator. We end up with $1,836.75. Alright, so why don't you try the next one? Try this one on your own, and then so pause it and then hit play once you're ready to go. So when we plug into our calculator, we have A of 5, meaning the amount of money you make after 5 years, equals, and this is P, this is R, so we're going to have 2,000 times E raised to the 0.065 times the 5 years. So when we plug that into our calculator, we should get $2,768.06. Alright, so now we're going to work with the natural log function. So we're going to do the same thing like we did with e, but we're going to plug it into the natural log of x. So we're going to have natural log of 2. And that's in the same spot on your calculator as the e was, but we don't have to hit the second button this time. So once again, we're just going to hit natural log. So we don't have to hit the second button this time. That's this guy right here, in case you want to see it a little bit bigger. We're going to hit natural log, and then we'll type in 2 and hit enter. So this one asked me to go to the nearest thousandth, so 3 decimal places. When I plug it into my calculator, natural log of 2, I end up with 0.693. So let's plug in the other one. So why don't you try that, plugging in 1/2 and plugging in -1, see what happens. When you're ready, hit play. So with the natural log of 1/2, I end up with -0.693, and that's kind of interesting. Think about when we were talking about negative exponents and how logs have to do with exponents. If you have a negative exponent, it gives you the reciprocal. So here I had 2, and then I get the reciprocal, 1/2, when this guy became negative. Okay, so this became negative, and now I have the reciprocal in here in the log. Now the last one, the natural log of -1, well, if you remember back to solving, we did the one-to-one property, we knew that, well, if I get a negative number, when I plug it back in, and it's the log of a negative number, it's not going to work. So this is going to be no solution here. You cannot take the log or the natural log or any kind of log of a negative number. However, you can raise the exponent. You have the x to the -3 or e to the -14. And negative exponents are okay, but taking the log of a negative number is not. Now let's take a look over at this graph that we have. This is e to the x, and this is natural log of x. They are inverses of one another. So much like the inverse operation, meaning multiplication, division, or addition and subtraction, or squaring and square roots, they undo one another. And that's going to tie into this next part here. So for this one, we have exponential form and we have logarithmic form. So e to the x equals 30 is exponential form. Logarithmic form is x equals natural log of 30. This is just an example with 30. You could do that with any number. It could be e to the x equals 40. Okay, so what we want to do is we want to change it from exponential to logarithmic so we can see how that works. The way that I like to go about doing this is, well, since I know that natural log and e are inverses of one another, they cancel each other out. If I take the natural log of each side, I'm going to have natural log and e cancel out, and I'm just going to be left with that x right there. So I'm left with x equals the natural log of 30, which is exactly what I wanted over here. So I got exactly this. This is just going from exponential to logarithmic, logarithmic to exponential. The directions will tell you which one to do. All right, next we want to get it into exponential form, so I want to have the e involved. Well, I'm going to have to do e raised to the x and e raised to the natural log of 30. And once again, these two cancel each other out, so I'm left with e to the x equals 30, exactly what I started with over here. So now I'm back into exponential form. Alright, so let's try this with a couple problems. So it says write an equivalent logarithmic or exponential equation. Well, if I have the e there, I know that's exponential, e exponential, and I want to get the logarithmic part in there. So I have to take the natural log of both sides. So I have natural log and natural log. The e and the natural log will cancel out, and I'm left with 4 equals the natural log of 54.598. And if you were to plug this into your calculator, you'd get something that's about 4. Of course, it's not going to be exact because this has been rounded over here, but you get something about like 4. Now, for number 2 here, I'm going to raise both sides with a base of e. So I have e to the natural log. Well, that cancels, and I'm left with 403.429, and that equals e to the 6th. So why don't you try these next two on your own, so pause it, and then we'll go through them. Alright, so what I'm going to do here is I'm going to take the natural log of each side because I have the e and I want to get rid of that, and I get 1/3 equals natural log of 1.396. And lastly, raise both sides with a base of e, and I'm going to get 1/4 equals e to the negative 1.386. And this is okay that this is negative because it's an exponent. If it were natural log of negative 1.386, that would not be okay. Alright, so this is a little bit different than what we did before. This is starting with day 2 now. We want to see how long will it take to double an investment. So we're going to be using our compounded continuously formula. But it says a $1,000 investment earns an interest rate of 7.6% compounded continuously. How long will it take to double the initial investment? Well, if I want to double the investment, I know my new investment is going to be $2,000. So $2,000 equals, and now I just plug in what I normally would, 1,000, e raised to the 0.076, but I don't have a value for t. I don't know what that is, so I'm going to use that still as a variable. So I'm going to have t, and I put that in blue so I know that's what I'm looking for. Now for this problem here, we need to solve for t. And because it's up in the exponent, I can't just divide by 1,000 e to the 0.076. I have to do a little bit more. But I'm going to start with dividing by 1,000. And I'm left with 2 equals e raised to the 0.076 t. Now, like we were just doing in those last problems, I can get rid of the e by taking the natural log of both sides. So I have the natural log the natural log of 2 equals 0.076 times t. And I can get rid of this coefficient here, the 0.076, by dividing. So this right here is what I'm going to plug into my calculator. Now when I plug that in, make sure that you are closing off your parentheses around that 2, otherwise you will get an incorrect answer. And once we solve that, we get t equals 9.12 years. So just over 9 years it would take for that investment to double. So why don't you try this one now. Pause the video and then I'll go through it. Alright, so for this one, I have 4,362.94 equals 2,000 e to the 0.065 times t, because I don't know how long it will take to earn that amount of money. So I'm going to do the same thing, divide by 2,000, and I get about 2.18. That's rounded, so our answer will be a tiny bit off, but it should be pretty close. And then I'm going to take the natural log of both sides. And I have the natural log of 2.18 equals, so these cancel, 0.065 t, and I divide by 0.065. And I end up with t equaling, don't forget about your parentheses here, t equaling about 11.989, so we'll say about 12 years. And that's it for that type of problem. Alright, for these last few problems, it's basically just change of base here. So I'm going to have, we can use natural log if we want, natural log of 38 divided by natural log of 5. And we end up with 2.26 for our answer here. Once again, here, same thing, natural log of 145 divided by natural log of 8. Feel free to pause this video at any time and try these problems on your own. And we get 2.39. And then for this one here, once again, change of base. So I'm going to have the log of 12 divided by log of 5. And I end up with 1.54. And then the last one, a little bit different. I want to make sure I do change of base with this, and then I add 6 to that. So I end up with, when I do change of base, I have log of 39 divided by log of 4, which gives me 2.64. And then I add 6 to that, so I get 8.64. And those are my final answers. So that's it for the lesson. There's 2 worksheets. Day 1 is a worksheet from the book. And then the second one is one that us teachers made. So you can find those on the website, and they are labeled accordingly.